You can do wonder on conventional thing. Think about only, like very new molecules. You can look at the existing systems, you can improve the performance of that, right? We all know about zinc coatings. You just go walk around, they are galvanized sheets, right? You will see galvanized sheets, the galvanized steel structures, hot dip. Zinc coating provides a very high resistance corrosion. We all know about it, right? Your company like a Tata Steel, they coat the steel sheets a few micron, let's say about 8 micron thick coatings, okay? If they can reduce 1 micron thick coatings, they can save millions of dollars because the zinc costs very low. Can you reduce the thickness of the coating, improve the performance to a large extent? You can change the microstructures. I don't want to go into details. You can see the change. This is the zinc coating. You make some additions to this. The changes in the microstructures improves the performance to a large extent simply by adding a very small quantity of element like. Just add it. As told yesterday about scandium on aluminum alloys, you can have some strontium here. You can bring out changes in the microstructure and cause a significant improvement in corrosion. I show you the results here. Most of you will know the way you test the material is by salt spray. You coat this zinc coating, for example, you make a scratch, put them in salt fog. Salt fog test, right? This is a chamber where you atomize the sodium chloride solution, expose the sample to this environment here, and find out the time taken for rusting. Pure zinc, look at this. In 168 hours, you see the rust coming up here, right? Compare this with the alloy, 336 hours, 1556 hours, the rust start coming. You see the increment in the performance from 168 hours to 1056 hours here. Just add very small 0.02 weight percent strontium. That's what you do that. Because you understand the structure of that and you can bring out the change in the things. This is what we mean by conserving nature. So I don't have to waste any zinc now. It costs more, but the resources of the earth is limited. So I can get the performance far better than otherwise you get here. You see, there is almost about 8 times increase in the performance by adding a small amount of that. How do you do that? You understand the microstructures. You understand the metals, how they behave. That understanding is important. This again is one PhD student. No, everything is one PhD student, which means there are a lot of stories behind what goes on. Please don't mistake me. I just present very nice results. There are a lot of hard work, a lot of failures happen in the research. It's just not that, I have only 2 slides, we started here, we ended here. No, research doesn't go that way. You always find the difficulties. You get results once in a blue moon, right? We call once in a blue moon. It is very much true for research. You work very hard. Of course, the once in a blue moon is very valuable. Your research is very valuable. So you struggle and struggle and struggle, and finally you get wonderful results. And we also looked at something very, very fundamental here. Okay? Let me go here. Okay. I think I have not put that here. Okay. No, yesterday we talked about, I think one of the faculty members talked about fatigue problems in aircrafts. When you have cyclic loading, the metal fails, right? So fatigue, stress concentration, you have heard of stress concentration. When you have a pit, we talked about a notch yesterday, the pit becomes stress concentration, the cracks starts at that location. So the pitting is the major reason for that. You make a pit. A pit is electrochemical. It's electrochemical corrosion. Film is getting damaged. You form a pit, and then that pit is causing the problem. So we understand this pit. See how we can really arrest it. Let me see if I can show that to you. cursor? Can I get the cursor here? Now it's coming. Yeah, thank you. It's coming. Yeah, yeah. I'm showing here. You see?
No, he wants to run the video.
Yeah, you see now how the pit is growing. You can see, you can able to see this location here, right? I can put it back. I put it back here. You see, there is, you observe the surface. Okay, observe the surface.
More to the left.
See how the current is changing. You see how this is growing now. So you can understand how this pit grows. And from that, we know the mechanism of heating. And we will suppress it now. Okay. See, the pit is now is now healed now. The current has come down. So this is called a metastable pitting, right? So we understand that kind of problems. This is called as spatio-temporal evaluation of the pits now. As the pit starts growing, okay, you can be able to understand. Maybe I think I'll skip this. Okay. Let me come to, so these are some of the work that we have been working on. Let me come to today's the talk. The main talk of this is on the oxidation behavior of the metals. These are the two students who worked on that actually. He has finished his PhD, he's working in the US as a postdoc, and he is able to complete his PhD work in a couple of months. The work was funded by the Department of Science and Technology and the Mission Mode project, and several people were involved. Let me go to the problem here. Why this problem is important? We generate power through steam, the thermal power plants we talk about, right? The thermal power plants generate steam at a temperature around about 250 degrees Celsius, the pressure 100 bar pressures, and that is called as subcritical boiling. You take the water, you boil them, you have both the liquid and the steam together taking place, right? But if I can pressurize it, heat it to 700 degrees Celsius, don't allow the steam to form. Keep the water in the same state, 700 degrees Celsius, don't allow the vapor to form, keep in the same liquid state. Then the heat transfer becomes extremely large. When you form a gas bubble, the thermal conductivity becomes a problem. Apply the high pressure, don't allow the water to evaporate, then the heat transfer between the fuel on the side and the steam on this side is very efficient. The boiler is very efficient way of transferring the temperatures, right? And that is called as supercritical, right? Supercritical temperature is 374 degrees Celsius and 22 megapascals. If you increase the pressure about 25 megapascal, you can contain it now, right? And then you can have a better heat transfer, and so the thermal efficiency is very large. Reduce carbon dioxide emission by that particular process. It is easier to said than. I have to take a boiler, right? I raise the temperature to 700 degrees Celsius. Okay? Look at the thermal efficiency. The thermal efficiency of a power plant. So that's what is normally we call about. Now, when you rise the temperature, the water is no more water. It is called supercritical water. It loses its property, it becomes non-polar. I hope you know that, right? The water is a dielectric. You put a salt, dissolves in water. At that temperature, the density of this water becomes very low. It becomes non-polar. Salts don't dissolve. They remain on this. And so the property of this water is changing. I will not go into details. The dielectric constant really becomes low, and the dissociation constant changes. All are really happening in the systems. That means now we look at water differently from the corrosion point of view as compared to normal water. It is not 500 degrees Celsius to high temperatures. The metal has to withstand the temperature. The temperature is 700, the creep, right? Most of you know, you take a lead, you hang it, the small load, lead will start sagging, right? Same thing happens to these materials at the high temperatures. They call the creep actually, right? The creep. They simply elongate. They don't retain its structural integrity. That is called as creep rupture problems. We talk about if 100,000 hours the metal can withstand a given load, that is the specification for any applications. Now, to look at this now, the creep rupture strength of 100 megapascal. Please look at, I only apply 100 megapascal. I don't apply more than that because at that temperature it cannot be applied. I apply only this. This is the load. I apply. Look at the temperatures. As I raise the temperatures, you cannot use the stainless steels here. You go to what is called a nickel-based alloys. Nickel-based alloys like 740, 617. Only these alloys can be used. You can't use any of these alloys at all. That is the first condition of material selection. Materials are not selected based on oxidation alone. The materials are selected by the temperature and the ability to withstand creep actually. So the selection of materials are based on the stability against the temperature here. So we need to now study whether they oxidized, resistance to corrosion, all this we study. So I'm going to spend some time. You please tell me when I can finish it.
I think this presentation ends tomorrow if we can talk.
I can listen to him for next week or so.
Actually, I'm talking, when I find it, when I'm chilling, I spend time. Because
I don't want to
No coffee. Go ahead.
justice to the next speaker. Thank you so much. So we look at these alloys. These are the alloys which are potentially usable at the temperatures. So somebody was talking the other day, what is the criteria for material selection? Corrosion is not the main one. It has to withstand the function. The function is that temperature and pressure, these are very good, but it has to withstand the temperature and pressure. So that's what happens. So we choose these alloys for the applications of this particular boilers. So again, it's very interesting now. The water is not same anymore. The temperature is so large, the water decomposes into hydrogen and oxygen here. They dissociate into oxygen radical here, right? Oxygen ions here. So the water is not the same water. That means it is going to now change its corrosion behavior differently because the water is decomposed into these species, and these species are promoting corrosion in the system now. So that's a real problem, right? So I'm going to just go. So what happens? You have alloy here, you have oxygen ions sitting here, so you find there is going to be an oxidation. These ions will react with metal and form metal oxides. Okay? This is called a supercritical water, and this is a problem that happens. Please see that there are free oxygen ions in this, and they sit on the metal surface, and then they start oxidizing the metal surface. Anyway, and so one more problem. You have a stainless steel, you just look around, there's a very thin film. Nothing happens. The same chromium oxide film at that temperature, they volatilize, they simply evaporate. Chromium oxide is no more protected. It changes the whole behavior of the material, right? It changes the whole behavior, and so you have other complexities in this. Otherwise, the chromium oxide is very good. A lot of stainless steels are being used where the mechanism of corrosion protection is to have the chromium oxide, but at that temperature, the chromium oxide simply evaporates. It's no more good at all for particular applications. So these are the issues that happens now, and so we start looking at it now. the problem was given to us, and by the government of India, and we took it as challenge because it is a corrosion guy working on this system is not very easy. So we need to first of all establish the system. So first of its kind in India actually, and we started working to develop a unit for carrying of the test. That was the first challenge for us. Now this is kind of the autoclave. This is high pressure. So water gets in here, rise the temperature. You have samples here. No problem. Issues are plenty here. The mechanical engineers know that if I am going to make an autoclave, work at high temperature, high pressure, I apply 100 megapascal, the wall thickness is this much, right? Heat transfer becomes a problem. The surface temperature becomes beyond the values. So you need to calculate the heat transfer and mass transfer calculations here to optimize the overall system here. So the optimization of the reactor so that you are able to get the temperature, you are able to get the pressure without any problems. Otherwise, the still temperature will be very high. You cannot really work on it now. So, of course, we collaborate. I don't want to again get into these equations. Most of the mechanical engineering department would know how to calculate all this, using these equations here. But finally, using all these equations, we're able to arrive at the thickness of the reactor so that the reactor can be very stable. You are able to reach the temperatures. So we have done it. First trial, we are very happy. We did the same work in the same company. We just went there. In fact, it was COVID time. My student was extremely good. He went and stayed in the place 1 month in COVID time. Food comes there, and so thanks to him. So he really struggled. As I told you, it is like a marriage function, right? That day is very happy. But before marriage, you have to do so much of work. But that day is very good. So the day has come where you could able to see this, right? Able to raise the temperature and able to show that we are able to get the reactor at that particular temperatures. Now the water continuously has to go. It's not that I have water, close it at all. The water continues to move and it happens at all. So we are able to establish the system and so that we can able to undergo the corrosion process. This is the photographs of the systems that we have. Please notice it's autoclave here. It's a safe chamber. It is interlocked here. Once you turn on the systems, it interlocks. Nobody can enter here because the temperature and pressure is so high. Small thing comes, you're finished, and nothing can save the person from here. So you have autoclave system. You have water treatment. Water treatment is important. You can't use the normal water. The conductivity of the water is 0.1 microsiemens. You see here, 0.1 microsiemens water. The oxygen content is very low, 10 ppb. So they all the systems are all. This is called